Hey everyone, welcome back, and today let's solve Leetcode problem 21 titled Merge Two Sorted Lists. So we're given the heads of two sorted linked lists, list 1 and list 2. Now we simply want to merge the two lists into one sorted list, which should be made by splicing together the nodes of the first two lists. And we want to return the head of the merged linked list as our output. So in example 1, we have list 1 and list 2 to be nodes 1, 2, 4, and node values 1, 3, 4 respectively. And in this case, if we merge both of those lists or individually, more contextually, splice nodes accordingly at each iteration from both lists to get a sorted list, we'd see we get 1, 1, 2, 3, 4, 4. Notice how not only is it sorted, it has the combined node values from list 1 and list 2. Right, and of course they're spliced and put in the order of non-ascending or increasing strictly order. And rather not strictly, but just increasing order. In example 2, both our lists are empty. We don't have any nodes, and hence our output is also not going to have any nodes because there aren't any nodes to merge, combine, and sort. And so that's a very straightforward output. Finally, for example 3, another rather straightforward example. List 1 is empty. We only have one node value of 0 in list 2, and so that's also going to be the only node or node value we have in our resulting list, the only node we have in both lists combined. So for the constraints here, we see that the number of nodes in both lists are always going to be in the range from 0 to 50, which is rather small for input constraints, at least relatively. And any node value is always going to be between negative 100 and 100, where both of the lists are always sorted in non-decreasing order. So not only do we have to combine them in non-decreasing or ascending order, we're also given the fact that both of those input linked lists are also going to be given to us in ascending or non-decreasing node value order. Which leads us to the main observations that we should really make to solve this problem. And the first one is, well, what we just talked about. Let's go back to this. Let's just go back to what the problem told us. It said that both lists are already sorted in non-decreasing order. Both of our inputs are already kind of perfect in the sense of already being in the form that we want our output to be in. And so how do we actually take advantage of that property? Well, that tells us that, okay, we don't need to actually sort our individual lists input again. We really just have to merge them with the smaller values coming first. And we know that the smaller values are always going to be at the beginning of each linked list. And we're going to do that like two pointers walking through or iterating through the lists as we individually pick according values or other smaller values at each iteration to put first in our sorted final output linked lists. And so this is a very straightforward pointer or iteration problem, and there actually is also a recursive version for this, but in this case we'll use, in my opinion, and generally the easier to understand and more memory efficient approach, which is really just the iterative approach with our two pointers for our two linked lists. So let's go ahead and begin how we can actually start talking about how we can actually solve this in the most efficient manner. So what is list node? Well, basically, it's really just the class or building block of our linked list. It's how we actually instantiate objects and actually build off nodes in our linked lists with default values and next pointers. And for our dummy node, we'll be using something called the dummy node. It's actually a very common technique when solving linked list problems to simplify linked list operations between nodes and next pointers. And we'll also have a current pointer to actually build the merge list iteration by iteration or step by step as we actually choose smaller values to come first in the sorted linked list. So let's go ahead and actually start with the code here. So like I was just talking about, we're going to have our initial dummy node or dummy object. So I'm literally just going to call it dummy, and it's going to be an object, or rather, an object of list node. And for our parameter here, we're going to pass in 0, right? Basically, you can also think of this as just a new dummy node, right? It doesn't really hold any meaningful value to us. Really, it's just a placeholder to actually start building our new list. Hence, we actually instantiate it with the list node starting off with 0, right? So we're going to use the value 0. But it really could be anything, right? Again, this is just a placeholder value. We can put 1,000,000 if you really want. It doesn't really matter. This is just to actually start building our new fully formed sorted list, right? So now let's actually create our pointer and instantiate it from where we're building off of from. And of course, we're building off from dummy. And so we're going to start from dummy and set our current pointer or our our current pointer that we're going to use to build our merge list to be dummy, right? Basically, it's going to initially point to the dummy node, and we're going to create this pointer to help build the merge list step by step throughout iterating through both lists using, again, that pointer technique. Right, and we're really just starting off from dummy, but building off from there and onwards, right? And it's always going to point, and again, when I say it's always, I mean current. Current's always going to point to the last node in our merged list as we build it, because we, of course, build it iteration by iteration, and we choose when to actually pick values from it through both lists input. So now let's actually begin our kind of main iteration of going through both lists, and I'm actually going to use a while loop to do this. So while, and give me a minute. So while list 1 is basically non-null, and the same applies for list 2, meaning as long as both list 1 and list 2 are not none, basically while they're not none, we can still keep looping or iterating through both of these input linked lists while we still have nodes to process in both lists. We haven't processed all the nodes in both lists yet, hence they're not none yet. And while we still have nodes to process, we're going to keep going through this while loop and iterating or pointing through each of these nodes, right? So here's where we actually choose which node value from which list that we actually want to choose to put in our currently building, or the sorted array that we're currently building, to make it in sorted order. So if the value at list 1, or rather the current value in list 1, if that's smaller than the current value at list 2, well then what do we want to do? Well, let's think about what sorted order really means. At this current iteration, or at this current point, we're comparing the two current values between list 1 and list 2. And of course, we want the smaller values to always go first, or always go in the earlier part of our sorted, fully built merged array. And so if list 1's value is smaller, we know that wants to come first because it has a smaller value, and we want to make it in sorted order. And so if list 1 is smaller, well then we'll actually choose the smaller load and add it to our merged list. And so we'll set current.next, where again current is going to point to the last node in our merged linked list, and we're going to set that now to be equal to list 1, because again we're basically simulating attaching list 1, or the list 1 node, to current.next, meaning we're choosing the smaller node because we want our final merged list to be in sorted order, and we're actually adding it to our merged list. And after we actually kind of add it to our merged list, we want to then take list 1 and, well, update it as well. And so we're going to take list 1 and move it to the next. Because we've already just used this current value in list 1, we want to go one more. We want to kind of move our pointer forward because we've already used the current list 1 node, as we've already established that it's a current node that's smaller that we actually have already added to our merged list. And so we want to actually look at the next node, or node in list 1 in the next iteration, and compare that in the future operations. Now, this whole if statement was all for if the current value in list 1 was smaller than the current value in list 2. What if that isn't even the case? What if list 2 current value is smaller or equal to list 1? Well, then we want to take that first instead, because again, we want the smaller values to come first to instantiate or make sure that our merged linked list is in sorted order. And so if list 2 node's value, or rather if list 2's node value is smaller, well then let's take that. And so very, very similar operation to what we did here, except we're going to be doing it with list 2 node's value, right? So we'll set current.next, if this is the case, to actually be list 2, and move forward in list 2 to explore the next node, which is basically just setting list 2 to be list 2.next, right? We're basically removing list 2 forward to its next node after attaching it to the current.next instead, right? And finally, kind of like the last operation, if you will, in this while loop here, every single time, we don't care which node or which list we attach the node from to our current merged list. We have to always move our current node forward. And so we'll set current and update it, of course, you guessed it, to current.next, right? Because in each iteration, regardless of which list we actually applied or merged the node from, or which node we actually attached, we have to always move this current pointer forward because it's going to point to now the last node in the merged list so far. And so we always have to move it forward to now point to this new last node in the merged list so far, regardless of whether it's from list 1 or list 2, based on whichever one was smaller. And once one of the lists is completely processed, we'll then of course break out of the loop. And once we know one of the lists full, all nodes are gone, we only have to take care of the remaining nodes in the other list. And so once this while loop is actually done executing, well, then we'll get to current.next. And here's where we're kind of taking care of that. We'll update it to be list 1. Well, we only want it to be list 1 if list 1 is non-null, right? Basically, if list 1 still has nodes that we haven't taken care of. If list 1 is null or is none, that means great. We've processed all the nodes and added all the nodes from list 1 to our merged linked list. We don't care about this input anymore. We then have to set it to list 2 because we only want to take the nodes from whichever list that we haven't fully processed to make sure that, of course, those are the largest values that have to come at the end of our merged list array, right? This is the main, really key line of our solution here to make it very efficient, right? If list 1 is not none, we have to attach the rest of the nodes that we haven't processed of list 1 to current.next. However, if it is real none, if we've processed all the nodes there, well, then we simply just attach the remaining nodes in list 2. And since our input lists are sorted, we don't even need to care about any more comparisons. We just need to connect the remainder nodes that we know are the largest throughout both of the inputs at the end of our fully merged linked list, right? We just have to connect it back to our output. And effectively, to actually return our output, we want to return dummy.next, right? This is kind of where our dummy kind of placeholder comes back into play, right? We're returning dummy.next because dummy was, again, just a placeholder. The real head of our merged list is actually going to be stored in dummy.next because that's how we actually instantiated it, right? That's where the real head is actually going to be stored, right? So if I were to submit this, this should actually be accepted unless I made any syntax errors here. Okay, let's see what I did wrong here. Dummy equals list node at 0. Probably just a very, very silly syntax error here. Okay, yeah. So clearly I forgot to capitalize my N. I did not realize that. Okay, clearly the N was capitalized here in the class. Sorry about that, guys. But as you can see, now this really works, and it is the most efficient solution possible. So on a high level, how are we really solving this problem? Again, it's a very simple iterative pointer technique where we simply iterate through or kind of walk through both input lists at the same time with one singular while loop, and we always pick the smaller value at each step to ensure that we have a sorted or non-decreasing or ascending order merged linked list. And we're always building a brand new sorted linked list as we actually went. And once, one list ran out of nodes, we simply attach the rest of the nodes of the other list at the end of our merged linked list because we would have concluded that they would actually be the largest nodes throughout both lists. And it actually is as efficient as you can get because we're really just using 2 pointers and a dummy node to simplify all these linked list operations and keep it as simplified and as efficient as possible. Which brings us to the complexity of this solution. So for the runtime complexity here, as you may have imagined, it's a very standard big O of n plus m. N is going to be the length of list 1 and m is going to be the length of list 2. Why? Because we're really just going through each node in both lists exactly once, not more than once, not less than once, with one singular pass or one singular iteration, and so it is really just the sum of the sizes of those 2 inputs. And for the memory complexity, believe it or not, it's actually going to be big O of 1 or linear. We're not actually using any auxiliary memory or any extra data structures. We're just using a few integers and a few dummy placeholders like dummy and current, right? Really just reusing the nodes from the input lists and just adjusting our pointers as we iterate through them. And again, the only extra space are these few integer pointers like current, but that's not really going to affect our memory complexity or our space. And so it is actually going to be a constant space. And so that's going to be it. That's going to be big O of 1 or constant memory or space complexity. If you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.